So the big theorem about vector spaces says if a vector space V has bases, two different bases, B1 and B2, with the cardinality of B1 equal to, let's say, N1 vectors, and the cardinality of B2 equals N2 vectors, then in fact, N1 is always equal to N2. And the dimension of a vector space is the number of vectors in a basis for the vector space. And you remember a basis, B, is a basis for a vector space V. V is a set of vectors. If B generates V and B is linearly independent. So these are the key ideas about a vector space, the most fundamental ideas about a vector space.
What about question D?
Well, yeah, I don't have the version of the text that you do, so you have to tell me what the problem is.
Yeah, we have three vectors. The first one is 1, 1, and 1 minus 1, and minus 1, 1.
1, 1.
And 1 minus 1, and minus 1, 1.
Okay, so these are contained in R2. So the quick way to solve this problem is R2 has dimension 2. So any three vectors in R2, any three, must be linearly dependent. So we know these three vectors are linearly dependent because a two-dimensional space cannot contain a three-dimensional space. Let's just look at the first two vectors. Maybe they're independent. Take 1, 1 and 1 minus 1. So suppose some linear combination is 0. What is this vector? This is x plus y, x minus y. If that's 0, then x plus y equals 0, x minus y equals 0. If you add, you get 2x equals 0, so x equals 0, and so y equals 0. So these two vectors are linearly independent, and the subspace these three vectors generate has dimension 2. It has dimension at least 2 because they're two linearly independent vectors, and it can't be 3 because there are no three different vectors in R2 that are linearly independent. So is there more about that I should explain?
Could we like try?
Thank you, it's clear.
Sorry. Could we try one more example if somebody has like another one from the homework? We just try one more. Or I guess I could just ask my question. So because it's in R2, right? We can't it would need to be linearly dependent. But you're saying that the first two, the 1, 1 and the 1 minus 1, are linearly independent because of that problem, like the
Well, I
score.
proved it. So the only linear combination of 1, 1, and 1 minus 1
Yeah.
gives you the 0 vector
Mhm.
occurs when both x and y are 0. And that's the definition of linear independence.
So why do we disregard, or why aren't we involving that third?
Well, I didn't need to. I know that these three are linearly dependent. So the
Mhm.
question is, are two of these linearly independent? I just tried these two.
Okay.
If it didn't work, I would have had to try, look at other possibilities. But it
Mhm.
just turned out these two worked. In fact,
Mhm.
any two of these three vectors turn out to be linearly independent. And actually, that's not true. I mean, these two vectors are not linearly independent because if I take the vector 1 minus 1 and I multiply it by the scalar minus 1, I get minus 1, 1. So these two vectors, one is a scalar multiple of the other. But these two vectors are independent of each other.
Mhm.
So, Professor,
Yes.
so if I understand what you just did is like the dimension is the number of vectors that are linearly independent, right?
No. No. So you have to say the dimension of what? So the dimension of a vector space is the number of vectors in a basis. And in a basis, the vectors have to satisfy two conditions. They have to be linearly independent and they have to span or generate the vector space. So for example, in R3, if I took the vectors 1, 0, 0 and 0, 1, 0, they're linearly independent, but R3 doesn't have dimension 2. These two vectors are linearly independent, but they do not generate or span R3. Right? Again, the dimension of a vector space is the number of vectors in a basis, and a basis is a linearly independent set of vectors that generates or spans the vector space. So two different conditions have to be satisfied in order to have a basis. So this is the fundamental concept about vector spaces.
Could we do, before we go on to the lecture, could we do number 8 from the midterm review? I mean, sorry, the exam 2 review.
Sure. So this is review problem 8. So we have S is a set of M vectors contained in the vector space V. And W, I put S in these brackets, this is the subspace of V generated by S. That means this is the set of all linear combinations of vectors in S. That's what a subspace generated by a set is. So suppose we let V1 up to Vn be a subset of W. And we want to prove that if the vectors V1 up to Vn are linearly independent, then n is less than or equal to m. So this is exactly a restatement of one of the basic results about vector spaces, which I can prove again, but the theorem we proved, I mean, we proved this as a theorem, but we proved it in the following sense. So we have a vector space V generated by a set S, where the cardinality of S is equal to M, and we have a set V1 up to V sub n contained in W, and we proved that if n is bigger than m, if you have more vectors in this set than vectors in the generating set, then the set V1 up to Vn is linearly dependent. And the contrapositive of that, so this says that if n is bigger than m, then this set is linearly dependent. So if we reverse that, that says that if this set is linearly independent, then n is less than or equal to m. And that's exactly this statement. So what we're asking for is a proof of this result. That's how I proved it in the notes, for example. And the way we proved it in the notes was as follows. So we have V sub I is in this set W spanned by S for I going from 1 up to n. And V sub I and W means every VI is a linear combination of the vectors in S. S consisted of these m vectors. So this was CI1 W1 plus CI2 W2 plus CI sub m W sub m. So so what I'm showing is that if you have m vectors that generate and n vectors in the subspace generated by these m vectors, then we want to prove these are linearly independent. So suppose some linear combination of these n vectors is 0. So just let me use sigma notation. So for so 0 is summation, j goes from 1 up to n, x sub j, v sub j. And let me put it like this. So vj is in w for j going from 1 up to n. So suppose I write vj, I know it's a linear combination. This is summation I 1j w1 plus 2j w2 up to mj wm. Or if I use sigma notation, this is summation Cij w sub I goes from 1 up to m. So W is a subspace of the vector space generated by these m vectors. So every vector in the subspace is a linear combination of W1 up to Wm. So for every j from 1 up to n, Vj is in the subspace So Vj is a linear combination of W1 up to Wm, and the coefficients are these C. Let me use A. Doesn't really matter, but Aij's. So if a linear combination of the V's is 0, then 0 is this sum. J goes from 1 up to M, x sub j, and every vector Vj is a sum Aij Wi, I goes from 1 up to M. So I have a double summation, and they're finite, so I can interchange. So instead of j from 1 to M followed by I from 1 to, this is j from 1 to N followed by I from 1 to M. I can write this as I going from 1 up to M and j going from 1 up to N, this times this, Aij Wj, Aij x sub j. Wi. This is a linear combination of W1 up to Wm with these as coefficients. And I want to know if all the x's have to be 0. If there's some choice of x's which are not all 0, then these vectors are linearly dependent, and that's what I want to prove. So I get the 0 vector here if each of these coefficients is 0. But each of these, setting this equal to 0, if I write summation, j goes from 1 up to n, Aij xj equals 0, this is just a linear equation. It's A1j x1, sorry, AI1 x1 plus AI2 x2 up to AIN xn equals 0. And I have, so this is an equation, a linear equation in n variables. And I have this for all my different values of I going from 1 up to m. A11 x1 up to A1n xn equals 0, down to AM1 x1 up to AMN xn equals 0. So this is a system of m linear equations in n variables. And the big theorem we proved about linear equations is that a system of m homogeneous linear equations in n variables always has a non-zero solution if there are more variables than equations, if n is bigger than m. And that's the case in here. N bigger than m implies there exists x1 up to xn, this vector, not all 0. So I can choose x is not all 0. That gives me this linear combination, so therefore the vectors are linearly dependent. So that is the big theorem about that produces the theorem on the uniqueness of the dimension of a vector space. Okay, so I don't want to spend more time on review. I want to start a new subject, not completely new, but the next topic, though, it's not on the exam tomorrow, but it certainly is on the final exam. And this is what we call invariant subspaces. So here we're looking at a linear operator. So a linear operator is a linear transformation from a vector space to itself. So whenever we use the term linear operator about a function, it's from a vector space, not to a different vector space, but to the same subspace. And we say the subspace W contained in V is T invariant or invariant under T if T of W is contained in W. So let me give an example. Suppose we take T from R2 to R2 given by the following matrix. T of xy is yx. So T is T sub A for the matrix A equal to 0, 1, 1, 0. So this is just the linear transformation. If it sends xy to yx, geometrically in the plane, if you take a vector xy, the vector yx is what you get by reflecting through the line y equals x. Right, this linear transformation. And suppose I take W to be the subspace generated by the vector 1, 1. Here's the vector 1, 1, and the subspace that vector generates, all scalar multiples. Scalar multiples of a vector, that's just a line. So this is just the line y equals x. And this is a subspace. And if I take any vector in this subspace, let me call this x. So if W is in W, then W is just x over x for some x. And T of W, which is T of xx, it reverses the coordinates, but they're the same. So when you reverse them, you still get xx. So every vector, if W is a vector in the subspace W, then T of W is contained in W. So W is an invariant subspace. And the most interesting, the fundamental or the simplest invariant subspaces are like these. They're one-dimensional. So we are interested especially in one-dimensional invariant subspaces. So that means if W is the set of all multiples of a vector W, that means that T of W is contained in W. And everything in W is a scalar multiple of the vector W. So T of W is some number lambda times W for some scalar lambda. So this is what we're interested in. And we have a special terminology for this. A number, a scalar, lambda is called an eigenvalue. It's a German word that just stands for special value. It's called an eigenvalue for the linear operator T if there exists a vector W or V in V, which is not 0, and T of V is just the scalar multiple of V. This vector V is called an eigenvector. So we're interested in trying to find the eigenvalues and eigenvectors of a linear operator. That's kind of the name of the game. So let's look at some very simple examples. Suppose I take the matrix 3, 0, 0, minus 2, and t sub a of x, y, this is from R2 to R2, is going to be a times xy. That is, you multiply the matrix times the vector, you get 3x minus 2y. And then you can notice, if we let E1 be the vector 1, 0, then t sub a of 1, 0, when you plug in x equal 1 and y equals 0, you get 3, 0, which is 3 times 1, 0. So if I let v be the vector 1, 0, and lambda be the number 3, this says that t of v is 3v, or lambda v. So 1, 0 is an eigenvector with eigenvalue equal to 3.
Professor, can there exist an eigenvector without an eigenvalue?
No, you can't have one without the other.
Oh, okay.
To say that a number is an eigenvalue means there exists an eigenvector v such that t of v is the lambda times v. And to say that v is an eigenvector means there's an eigenvalue lambda such that t of v is lambda v. You can't have one without the other.
Just one second. So how did we find that the eigenvalue was 3? Was it because the 3 was pertaining to the oh, never mind, you put let E1 equal 1.
Well, this is an easy example.
Mhm.
So I could tell by looking that E1 is an eigenvector with eigenvalue 3.
Yeah,
And if I let E2 be 0, 1, this would be an eigenvector with eigenvalue minus 2.
got it.
But
Okay.
that's only because this is such an elementary, simple looking matrix.
Mm.
All right. So let's take a more interesting example. Suppose I have the following matrix. Let's say A is equal to what's a good example? Now, let's just try this matrix. See, it's hard to find examples that are going to work easily. Let's try this. So here's a matrix, 4 minus 2, 1, 1. And so my linear transformation will be 4 minus 2, 1, 1 applied to xy. So that's 4x minus 2y, x plus y. So this is my map from R2 to R2. And it sends xy to 4x minus 2y, x plus y. And we want to find eigenvalues and eigenvectors. So suppose lambda is an eigenvalue. That means that t of xy will be lambda times xy. That's the definition of an eigenvalue. Lambda is an eigenvalue if there's a non-zero vector, so xy can't be just 0, 0, that satisfies this equation. But what is t sub a of xy? That's 4x minus 2y, x plus y. And the question is, can we find x and y such that this is lambda times xy, or lambda x, lambda y? So we actually have to find 3 different numbers, lambda, x, and y, to satisfy this. So 4x minus 2y equals lambda x, and x plus y equals lambda y. Let's see, if I rearrange that, this is 4 minus, well, let me bring everything over to the other side. This is the same as lambda x minus 4x plus 2y equals 0, and minus x plus lambda y minus y equals 0. I just brought everything over to this side of the equation. This is really lambda minus 4 times x plus 2y equals 0, and minus x plus lambda minus 1y equals 0. So I want to know whether I can find for some lambda non-zero x and y's that satisfy this equation. Now, what you're supposed to have learned in high school is if you have ax plus by equals 0 and cx plus dy equals 0, the only solution is 0, 0, and that only happens precisely when the determinant AD minus BC equals 0. Right? So this is high school algebra. If you have 2 equations and 2 linear equations and 2 variables, if the determinant of this number AD minus BC, is different from 0, then x and y have to be 0 to be a solution. But if AD minus BC equals 0, there's a non-zero solution. So in this system of equations, this is my A, this is B, this is C, this is D. So what is AD minus BC? A is lambda minus 4, D is lambda minus 1, minus B, which is 2, and C, which is minus 1. So this is lambda squared minus 5 lambda plus 4 plus 2, lambda squared minus 5 lambda plus 6. When does that equal 0? Well, this factors. This is lambda minus 2, lambda minus 3 equals 0. So for lambda equal 2 and lambda equal 3, I can find a non-zero solution of these equations. So the only possible eigenvalues are 2 and 3. Right? So let me go through this argument again, because this is a basic argument, which is a nice combination of what you're supposed to learn in high school, certainly in pre-calculus, and linear algebra. So here we have a linear transformation from R2 to R2. It sends the vector xy to 4x minus 2y, x plus y. And xy is an eigenvector with eigenvalue lambda if t of xy is lambda times xy. T of xy is this vector, equals lambda times xy, that's lambda x lambda y. That corresponds to just, for certain lambda, you can have a non-zero solution of these equations, which is exactly, if I just rewrite it, as this. And these equations have a non-zero solution if AD minus BC is 0. And AD minus BC is this. And that's 0 when lambda is 2 or 3. So this tells us that the eigenvalues for this linear operator are 2 and 3. And now we have to see if we can compute an eigenvector. So again, this is my operator. T of xy is equal to 4x minus 2y. That's the first coordinate. And the second 4x minus 2y is x plus y. And we want to know whether for some x and y, this is equal to 2 times xy, because our only two possible eigenvalues are 2 and 3. So I'm just trying lambda equal to 2. So this is the same as saying 4x minus 2y equals 2x, and x plus y equals 2y, which is the same as saying this is 2x minus 2y.
Can you bring your paper down a little bit?
Oh, sorry.
Thank you.
So this is my operator, 4x minus 2y, x plus y. And I want to know whether this is 2 times, whether I can find xy so that this vector is 2 times xy, the vector xy. This just says 4x minus 2y equals 2x, x plus y equals 2y. This is the same as 2y minus 2x equals 0. This is the same as x minus y equals 0. These are the same equations. X equal y, for any x equal to y, that's a solution. So for example, if you let x equal y equal 1, what is t of the vector 1, 1? It's 4 minus 2, 1 plus 1. That's 2, 2, which is 2 times the vector 1, 1. So we have t of xy equals lambda xy for lambda equal to 2 and xy equal to 1, 1. So this is the eigenvalue. And for that eigenvalue, this is, it's not the unique eigenvector, but this is the eigenvector. This is an eigenvector. The other possibility for an eigenvalue was 3. So suppose you want to find t of xy, which is 4x minus 2y, x plus y, equal to 3 times xy, which is 3x, 3y. So then 4x minus 2y equals 3x, and x plus y equals 3y. This first equation is the same as x minus 2y equals 0. This equation is also the same as x minus 2y equals 0. So whenever x equals 2y, we should have a solution. So you could have x equal to 2, y equal 1, because x is 2y. And let's experiment. Take t, apply it to the vector 2, 1. So when x is 2 and y is 1, I get 8 minus 2 is 6. And when x and 2 and y is 1, I get 2 plus 1 is 3. And you know that 6 is 3 times 2, and 3 is 3 times 1. So t of the vector 2, 1 is 3 times 2, 1. So here lambda equal 3 is an eigenvector value, and 2, 1 is the associated eigenvector. So this is a new way of looking at linear operators. You want to see if you can find invariant subspaces. That makes the study of the linear operator easier, and the simplest invariant subspace would be one-dimensional. And in the traditional language of linear operator and chemistry and physics and everywhere else where linear algebra is applied, it's very important to find the eigenvalues and eigenvectors. And we just looked at a couple of very simple examples in the case of a two-dimensional vector space. So that really is the new idea for today. Any questions about this at this point?
I just kind of got lost a little. Why do you set x minus 2y equals 0 and the other one below it as well?
Over here?
No, below that.
Here?
Yes,
This
yes.
is x minus 2y equals 0. I'm solving these equations.
Oh, okay.
Here's my linear operator. T of xy is 4x minus 2yx plus y. I want to find xy such that this is 3 times the vector xy, which is 3x, 3y. And for these two vectors to be equal, this coordinate has to equal this coordinate. So 4x minus 2y equals 3x. And similarly, this coordinate has to equal this coordinate. So x plus y equals 3y. And both of these equations are equivalent to x minus 2y equals 0. So whenever you have x and y where x equals 2y, you have a solution of this. The simplest is if you take y equal to 1 and x equal 2. You can take anything you like, but that's the simplest, I think. And you get this vector 2, 1, and you see that t of the vector 2, 1 is 3 times the vector 2, 1. So this is an eigenvalue, and here's the corresponding or the associated eigenvector. That is the story.
So this only works for invariant subspaces.
Well, no. So an invariant subspace can be of any dimension. An eigenvector gives you a one-dimensional subspace, and the one-dimensional subspaces are always the simplest.
Okay. One-dimensional.
But you can have more complicated invariant subspaces, but
It'd be harder. I kind of like this.
well, yeah, it's very interesting. And there's a huge amount of investigation of eigenvectors and eigenvalues, and it comes up everywhere in science where mathematical models are applied. You'll find this certainly everywhere in physics and chemistry and population biology. And if you want to make a lot of money and you go to Wall Street, you will, there are mathematical models of financial operations, and you want to figure out a strategy to make money for yourself and your company, and somehow knowing eigenvalues is part of the process of doing that. But just from the, I mean, I have no interest in that, but just from the point of view of pure mathematics, it's very, very, very nice. Okay. That is it for today. I will be back at 10 o'clock tomorrow. And the exam is at 3 to 5 tomorrow.
Are you gonna have the Zoom again too for the exam?
Sorry, am I going to what?
Have Zoom again, like during the exam hours?
Well, I'll be on Zoom, at least in the beginning, when you're looking over the exam, if you have any questions.
Okay.
I mean, and if for some reason I'm not responding to Zoom, you can also send me an email. And I'll definitely see one or the other.
Okay.
But at least for the first hour or so of the exam, I try to stay on Zoom so you have a chance to look over the exam and in case there's a question about something.
Are there gonna be 6 questions too this time?
It'll be similar to the last one, 6 plus or minus 1.
Okay.
I mean, but it's not going to be 20 questions.
Okay.
Of course, I could have one problem with 10 parts, but I'm not going to do that either.
Okay.
No, when I get my calculus exam, like one question might be, here are 4 functions, find their derivatives, and you write them down. So, there are lots of parts, but it's supposed to be pretty quick. But in linear algebra, very few problems are really quick.
Yeah.